chapter 5, you will be dealing with a complex loading of a beam, and your job is to quantify the stress because of bending. These sketches are common in mechanical engineering design. When you design your product, you may be faced with this structure in which your beam is loaded with a distributed load, a concentrated load, and you would like to know, let me repeat, you would like to know where inside the beam the maximum stress is generated. The beam is loaded complex, with a complex mode. The question is, at which location the beam will fail first? Or at which location, at exact location, the beam is very prone to fail? You would like to know. Because it is too complex, you need a methodology to solve this. First, I would like to introduce what we call as a transverse force. What is transverse force? Transverse is you are applying a force in a transverse perpendicular or parallel with the cross section. Transverse force. So, in the previous chapter, I demonstrated how bending load is generated by tensile, but this time, I demonstrate how bending stress can be generated by transverse load. All of these are transverse load because it is directed perpendicular with the axis. Okay? If you consider this beam and you have done the FBD analysis, from the FBD analysis you can obtain the reaction force at A and reaction force at B. I know that you're a master at this one, so I don't need to repeat this. After you obtain our A and our B, you would like to know the internal stress. Because you would like to know the internal stress, you are interested to find the internal forces. Okay? Now, when you cut over here, like what we did there, the reaction internal force would be X, Y, and M. That's it. But because the applied force are in transverse, there is no X anymore. We only consider two kinds of internal forces, which is the V and the M. The V, we call this as transverse force, or we call it as shear force. V is the shear force. The M is the bending load. Until this part, you should remember that the transverse force, when it becomes the internal, it becomes shear. Do you know why it becomes shear? Because it is applied perpendicular to the axis, therefore it is parallel with the surface. Thus, it creates shear. Okay? If in the previous chapter there is tensile and bending, both of these generated normal stress. In this case, you have shear force and bending. Bending will generate normal stress or shear stress? Normal stress. The V will generate normal stress or shear stress? Shear stress. So this will generate shear stress, this will generate normal stress. Two different loads, two different kind of stress. Okay? Now we will try to define the distribution of shear force and the distribution of bending throughout the beam. Now I would like to explain the convention. Listen carefully, yeah? Suppose I have this kind of beam. Then I'm doing a partition method. The partition method is done when there is a changing in load and changing in dimension. Remember? This is also similar with what you did in the uniaxial. When there is a changing in dimension, you do partition. When there's changing in, the load also changing. So if you do this, you might want to find a partition in this part, this part, this part, and this part. Before the applied load, after the applied load. Before the applied load, after the applied load. you would like to know what is the effect of that transverse force to the shear force distribution and the bending load distribution, bending moment distribution. Okay? Suppose you are doing a partition or sectioning method at C. This is the picture. Automatically, you will draw the positive convention like this one. We agree to have this rule. Okay? When you cut the specimen from the right hand side, what you will see as positive is this sign. V is going downward, positive. M is counterclockwise, positive. That is our convention. Now, if you decided to work from the right, therefore you cut to the left, you will see this. V is positive upward and M is positive clockwise. Therefore, this is how you remember it. When it makes a smile shape, it is positive. Meaning when you cut from the left, you will see this is a positive one clockwise. When you cut from the right, you will see this is counterclockwise, this one is positive. Yeah. This is how we usually remember the positive convention. And this is the effect, yeah. When you cut the right side, downward is positive. When you cut the left side, upward is positive. So this is how it looks like. When you do a partition cutting the right hand side, this is positive convention, downward and upward. This one is upward and downward. So upward and clockwise. Okay. Now let's discuss about this problem. For the timber beam and loading shown, draw the shear and bending moment diagram. What we are going to do is to check the value of shear force and bending moment before and after the load. Let me repeat. In order to construct SFD and BMD, we try to calculate the shear force and bending moment before and after the load. Okay? Now, let's start with number one. At A, there is a 20 kilonewton load. Then you cut this part only just to know what would be the shear force and bending moment after 20 kilonewton load. Apply positive convention, downward and bending moment. With this, sigma Fy, sigma M equal to 0, you can get that for this one, yeah. Vi, V1 is minus 20 kilonewton is minus, so minus 20 kilonewton minus V1 equal to 0, therefore V1 equal to minus 20 kilonewton. Done with this. For the M1, M1 is here, but the location is very near to the 20 kilonewton. This is it. The 20 kilonewton have a almost zero distance with the M. This is 1, 20 times 0 plus M1 equal to 0, therefore M1 is equal to 0. That is a location just near position A. And then you move to the next load, which is the support, 46 kilonewton. Before 46 kilonewton, you do it a partition. And then after, before, after. Okay? Before you do V2, M2. V2 is equal to minus 20 kilonewton. M2 is equal to 20 kilonewton times distance to position just before B. The distance is 2.5 plus M2. M2 is positive. So M2 is equal to minus 50 kilonewton meter. And then you move to the position right after B. At that position, the 46 kilonewton is observable. Before, no 46 kilonewton. After, there is 46 kilonewton. So V3 is defined by when minus 20 kilonewton plus 46 kilonewton minus V3 equal to 0. Sigma Fy equal to 0 minus 20 plus 46 minus V3 equal to 0. Therefore, V3 is equal to 26 kilo. Not minus. It's positive. So it is true that V3 is downward. V3 is downward because 46 is going upward. This is 20. This needs to be 26 to be in balance. 20, 26 against 46 balance. Okay? So you're done with this V3. The M3 is the same as M2 because it's still adjacent in an adjacent location in point B, just before and after. And then you move to the next load, the 40 kilonewton. You do it before and after. Before one, the 40 kilonewton is not seen. This one, after the 40 kilonewton is seen. So you do sigma Fy equal to 0, sigma F equal to 0. You can get every shear force and every bending moment at every location before and after the load. So you can get this value. You plot that value to find this. This is the SFD, the V1 and V2, yeah? V1 and V2 both are minus 20 kilonewton. Both are minus 20 kilonewton. Therefore, this one is still minus 20 kilonewton. Then V3, V4. V3 is 26, V4 is 26. So it goes to 26, 26. And the rest. Finally, it is 14. This is also 14. Close. So this is the shear force diagram, SFD. And this is the BMD, the bending moment diagram, also obtained from this value one by one. M1 is 0, M2 is minus 50 kilonewton meter. 0 to minus 50 kilonewton meter. And then M3, M4, let's see, M3 and 4. M3 is minus 50 kilonewton, becomes 28 kilonewton meter. Minus 50 becomes 28 kilonewton meter. So you found every V, every M in each position. Though that is the way, mathematical way, systematically, you can construct the SFD and BMD. From this condition, let me ask Jarvis, at which location the shear force is maximum? Jarvis? At which location the shear force becomes maximum? B2C, because this is the largest, 26 kilonewton. So you can tell that in between B2C, SFD give that shear force becomes largest. Michael, from the BMD, at which point the bending becomes maximum? Perfectly, exactly at B. It becomes minus 50 kilonewton meter. At C, it's only 28 kilonewton.
Yeah.
So, in combination, where in the B, the shear force and the bending moment reach maximum? John Island. Where in the B, the shear force and bending moment reach maximum? At B, because both reach maximum. 26, 50. So at B is the most prone to fail. Because shear stress because of V is maximum, normal stress because of bending is max. So that is why SFD in BMD is convenient. The loads are complex, but with this you can then evaluate at which location your beam needs an extra care. Understand everyone? Okay, in next meeting, I will go again with the SF and BMD with a more practical way before and after the load. Okay? Okay, I think that's enough.